The art of machine learning algorithms in predictive modeling in the realm of data science and artificial intelligence. Machine learning algorithms stand as the backbone of predictive modeling. These powerful tools enable systems to learn from data without explicit programming, making them indispensable across industries. This guide explores various types of machine learning algorithms that drive modern analytics solutions through practical examples and theoretical foundations. Understanding supervised learning methods. Supervised learning is a foundational concept where algorithms are trained using labeled datasets containing input-output pairs. This method allows models to predict outcomes based on historical patterns within training data. Different supervised techniques exist, each tailored for specific prediction tasks. Linear regression addresses continuous output variables by finding optimal relationships between features and targets. Classification problems benefit from algorithms like decision trees, which split data according to feature importance until reaching pure subsets at terminal nodes. Support vector machines, SVMs, maximize margins between different classes while minimizing classification error rates in high-dimensional spaces. Regression versus classification. Regression predicts numerical values, whereas classification assigns categorical labels to observations. Performance metrics. Mean squared error measures accuracy for regression tasks. Accuracy and F1 score evaluate classifier performance effectively. Exploring unsupervised learning techniques. Unsupervised learning focuses on uncovering hidden structures within unlabeled datasets lacking predefined outcome variables. Clustering algorithms group similar instances together based on distance metrics. K-means clustering partitions data points into distinct clusters by iteratively assigning samples to nearest centroids and recalculating cluster centers accordingly. Hierarchical clustering builds dendrograms representing nested groupings formed through successive merges or splits of subclusters using linkage criteria such as single linkage or complete linkage methods. Dimensionality reduction via principal component analysis transforms original variable space into fewer orthogonal components, capturing most variance within data. Data preparation. Normalizing inputs ensures equal weight distribution among all features during unsupervised analysis. Evaluation challenges. Since ground truth isn't available, silhouette scores measure how well-defined individual clusters are relative to others. Diving into reinforcement learning paradigms. Reinforcement learning differs significantly by enabling agents to make decisions through trial-and-error interactions rather than relying solely on static training sets. Markov decision processes provide mathematical frameworks defining states, actions, transition probabilities along with reward functions guiding agent behavior over time horizons. Deep Q networks combine deep neural networks with traditional reinforcement learning approaches to handle complex environments requiring large state action spaces. Policies govern how agents select actions given current situations, aiming to maximize expected cumulative rewards through exploration-exploitation trade-offs. Reward engineering. Designing effective reward signals remains critical since improper shaping might lead to undesired behaviors or convergence issues. Simulation environments. Platforms like OpenAI Gym offer standardized benchmarks facilitating development and comparison across reinforcement learning architectures. Analyzing ensemble methodologies. Ensemble learning improves model robustness by aggregating predictions made independently by diverse base learners working collaboratively toward final outputs. Bagging reduces variance primarily by averaging multiple weak predictors' results, exemplified best through random forest implementations involving bootstrap sampling combined with feature randomness. Boosting sequentially trains new models focusing specifically on correcting errors committed previously. Gradient-boosted trees illustrate this strategy very clearly when optimizing loss function gradients stepwise. Stacking enhances overall generalization capabilities by leveraging meta-learning strategies where secondary models learn patterns inherent within primary estimator ensembles themselves. Bias variance trade-off. Understanding this fundamental principle helps determine whether bagging or boosting would be more suitable depending upon initial learner characteristics. Computational cost. While ensemble methods typically require greater resources compared to standalone alternatives, they often justify investments due improved out-of-sample performances achieved. Examining deep learning architectures, deep learning extends conventional neural network paradigms considerably by incorporating numerous layers, enabling automatic abstraction extraction directly from raw sensory information sources. Convolutional neural networks excel particularly well at image recognition tasks owing to their spatial filtering mechanisms mimicking biological visual cortex operations quite closely. Recurrent neural networks specialize in processing sequential information, maintaining internal memory states, allowing previous context awareness crucial for natural language understanding applications. Transformers introduce attention-based self-attention mechanisms, providing parallelizable computation advantages ideal for long-range dependency management seen frequently in text generation scenarios. Activation functions. Choosing appropriate nonlinearities influences gradient flow dynamics, significantly impacting convergence speed and final model quality. Regularization strategies. Dropout regularization prevents overfitting by randomly deactivating neurons during training, thus encouraging distributed representations instead of reliance upon any single node's contribution. Comparative study of algorithm selection criteria. Selecting an optimal algorithm depends heavily upon several factors, including dataset size, feature complexity levels, along with desired application domain specifics. Scikit-learn provides extensive benchmark comparisons, helping practitioners understand relative strengths/weaknesses amongst common ML methods side by side visually. AUC-ROC curves help assess binary classifiers' discriminatory power, measuring true positive rate against false positive rates, varying thresholds systematically. Cross-validation methodologies ensure reliable estimation of test set performance, avoiding overly optimistic evaluations resulting purely from random chance occurrences. Interpretability needs. Some fields demand transparent models explainable easily. Tree-based methods generally satisfy these requirements better versus highly non-linear black box alternatives. Sensitivity to outliers. Certain algorithms become unduly influenced by extreme values, necessitating careful pre-processing steps, removing noise before proceeding further ahead. Evaluating real-world applications across industries. Healthcare leverages predictive analytics extensively, aiding early disease detection efforts, improving patient care standards drastically, especially regarding chronic condition monitoring programs. Finance industry utilizes credit scoring models, assessing applicant risk profiles, accurately predicting default probabilities precisely enough to manage loan portfolios responsibly. Retail sector benefits immensely from recommendation engines, personalizing shopping experiences, dynamically adapting suggestions continuously based on recent purchase histories actively. Manufacturing employs anomaly detection systems, identifying faulty equipment early, preventing costly breakdowns, ensuring consistent product quality. Maintenance standards remain intact always. Custom model development. Domain experts collaborate tightly with data scientists, designing specialized models addressing niche challenges uniquely found only inside particular sectors, respectively. Ethical considerations. Responsible AI practices mandate thorough audits, checking for potential biases embedded unintentionally within training corpora, affecting fairness metrics adversely sometimes. Conclusion. Mastery over diverse machine learning algorithms equips professionals with necessary skills required thriving successfully amidst rapidly evolving technological landscapes characteristically observed nowadays regularly. To stay competitive, developers must continually expand knowledge bases comprehending core principles underlying popular techniques currently dominating mainstream deployments worldwide ubiquitously today. HTML